Okay, so this lecture and the next lectures are not, it's actually going to be results, mostly demonstration of modeling approaches, some results, comparisons with experiments, and not all of them work I'm showing is mine. There are some other work like partially stirred reactors, thick flame, other closures, so you can see some comparisons of what the models do, just to give you an idea of where things are. So we're going to start with premixed and non-premixed, what I basically unswirled flames, and I already went through this to give you a basic concept of what the linearity model does, but also what typical G equation models may not do because it's difficult to get that. But now I will start to show more complicated rigs that are more of interest to us. So here's an example. It's called the Volvo rig. You may have seen it in papers. It's well known because there's a database for it. Essentially, it's a triangular bluff body in a test section, and it's premixed, and fuel is. And remember the point I was mentioning about partial premixing. Fuel injection is done upstream, but it is assumed that through this process you're getting perfectly premixed. I mean, that's an assumption because there's no proof, because as it happens, just like any other experiment, nobody measured anything there, so they measured stuff at the back. So numerically we have to assume it is premixed and basically run that, and then it's you get this flame structure on the back. You can see the image here, see some image there, and there was non-reacting and reacting. In non-reacting, the fluid mechanical sting is very different to the reacting case, and this is typically, so this was work done by Furby, and I've also done it, but you can see it has, there is a lot of comparisons here. The symbols are experiments, I'll show in a minute, but there's LES done by thickened flame, EDC, partially stirred reactor, G equation, and particle PDF method. So it's like same code with different models, And the idea was to see whether the models, what are the similarities and differences. These slides are available. The colors are not that great, but you can see from this that this is the mean. What is this? This is the mean velocity profiles. And that means you do the LES, you average it. I forget how many grid points this was. It's published in the papers out there. But what I wanted to point out is two things. One, that the models, on the average sense, this is at different locations. I think something is missing. You get the mean shear layer. So basically, these are profiles measured downstream, and you can see that some models are not very good. Like the G equation is a green line, and you can see by some places way off predicting the result. The partially stirred reactor in this problem is overall consistent, in this problem. Okay, I mean, but on the average they all look the same, and that's and the point here is that this is a low. It's not very high Reynolds numbers. This Reynolds number is 30,000 or to 45,000 based on step height. So it's but still a turbulent problem. So here is some more plots. This is the temperature plots, and in the temperatures you start seeing even more widely different results. Like the flame experimental data, and there are this experimental data in the symbols X and plus. Is what one of the issues is that one is gas analysis, one is LDV and cars. They don't agree. Experimental data don't agree either. So it's sometimes questionable what are we trying to compare to. But the main thing that is important to realize is that as the flame goes downstream, it is spreading in the experiments, and that is consistent. And some of the models do not predict the spreading correctly. There are errors in the prediction quite significantly as it go around, and if you read these papers, there are more details in it. And but then when we start looking at the RMS, that's when the problems show up. See, so the rule number one for LES is that the mean is never the question. You can generally get the mean by doing nothing. Sometimes it's not that. Remember, this is the average mean. Sometimes it looks, the flame is nice and stationary, you can get the average mean, but the RMS is where the trouble starts, because that is where the higher order statistics have to be predicted correctly. You can see that models are not picking up the core region. Some places the data is way opposite to the data, and so the question sometimes becomes is that when you compare, you have to check the experiment too. These experiments were done long time ago, 92, you know, and now nobody knows how they did it. You know, you have to take their word for it from their publication, and they have the data. And but then the modeling cannot match that. We can't go back. The experiment doesn't exist. We can go back to check something. And like I said, the question about partial premixing. Nobody knows whether it was perfectly premixed or not. You know, we have no idea no way to look at it. You know, we have also run this problem, and I just wanted to show some class flow physics just to show not too much. And this is a non-reacting case. You can see that we get the inertial range spectrum in the shear layer, and we actually were able to match. There's a shedding frequency of the structures I'll show in a minute, and the shedding frequency goes up in the reacting case, but we can still get the same spectrum. So the point was that the non-reacting and reacting still shows a peak shedding frequency, but what is interesting is that the structures are very different. So for example, this is a non-reacting case. You get the large scale structures that are forming. These are the one common shedding, the classical fluid mechanical one common shedding. But when it is reacting, it is much small scale. The large scales are killed by heat release, and you get the smaller structures in the shear layer that roll along the flame. This is the reaction flame front, and then only becomes much larger in the downstream. So this is what is typically understood that in premixed mixtures, if you have heat release and there is a big temperature jump across this region, then all the large scale shedding is eliminated. You get this, so you go from anti-symmetric shedding. This is anti-symmetric. Like for example, this is shedding on and off and on, off and on. Now that is gone once you have reacting, and you actually get symmetric shedding. You know, the flame becomes more symmetric, and typically they have shown that the jump across this, the temperature, unburned temperature to burned temperature. If it is around 1.8, it goes back to this, but if it is more than 1.8, I forget the number, it goes to asymmetric shedding. Lots of codes will not give you that. That's, you know, if you have a code, you should try that out, because this is a good example of it where the fluid mechanics is controlled by heat release in a very thin region. And if you don't have a good grid here, this was done with linear eddy model, but the point is that you have to have a good grid here even you're doing conventional LES, or you will get a shedding like this even for reacting. You know, but if you reduce the heat release, lower the heat release in the front for reacting, you'll go back to this. So just a couple of simple test cases. You can actually prove that even in 2D. You don't need to do 3D. Even though these are 3D, you can show that this happens. So this is an important point to mention, and this is some comparisons. Again, this was done. It was an old paper. So we actually compared EBU and LES to this. Again, if you look at the mean, everything reasonably looks, velocity field looks okay. We seem to have some differences. So one would argue that, hey, the EBU is dirt cheap. You know, it seems like it's doing a good job. You know, and to some extent it does a decent job. But when you start looking at some finer features, for example, here is the central recirculation bubble. The region that is predicted reasonably well, but when you start looking at the fluctuations, you start seeing variations between LEM and EBU. There are differences, but you know, so this is the RMS kinetic energy fluctuations on the axial distance from the block body. So again, the mean. A lot of times, this is very important from a design perspective. This is that bubble, because the velocity is negative behind the bubble. On the block body, and we need to know what that is to control that, but that is picked reasonably well, but the fluctuations are off. But then when we go to look at more fluctuation problems, like the mean actual velocity, like I said, comes out okay, just like in the Furby's work. But then when you look at Reynolds stresses, and some of the other turbulent quantities, you start seeing the differences, that the EBU is not predicting the shear layer physics very well. it's picking something, but it's not picking the right magnitudes. Now, if that's not important, we don't care. But if it is important, that becomes a problem. What is more interesting is that when you look at the heat release, which affects the temperature, you start seeing bigger differences. Like for example, this is the EBU result, while this is the LEM result. You can see that Christopher Furby's results also showed the same thing. The PASR showed the spreading better. It looks like the spreading is not captured by the EBU result. The question is why, and if you go back to looking at the flow physics, looking at the flame, so this is the premix flame, and these are all burned products. EBU basically is showing a symmetric picture. You can see it's a symmetric flame front, but the structures, all the structures, LEM result, instantaneous results from both. You can see the LEM is showing some wrinkled stuff, and this wrinkling is making it spread. So when you take an average of this picture, it shows this looks pretty much like a steady state. That's pretty much all you get. So if you look at that picture and compare it to this, you can see that the wrinkling makes the spreading more. So in the average sense, you got getting a spreading of the temperature, while the EBU does not show that, exhibit that. So even though qualitatively it has the right physics and it's much cheaper, obviously, at the same token, it is missing some fundamental physics that you have to be careful about. So if you're just happy with that, that's happy, then you're okay. But at some stage, if you change something, that may not change at all. Well, you might change this one. That's the point. Okay, that was just to show what the models do. Yes. Well, non-reacting was the only results. Yeah, we have results on non-reacting. It was published in somewhere in AIAA in 2005. Non-reacting, we got the shedding and then the spectrum, and there were some mean velocity profiles. That's just the fluid mechanics. So you have to make sure the grid you pick does the fluid mechanics reasonably well. So if you look at all the papers in publication, if they do non-reacting and reacting, they will say, well, we ran the non-reacting with 1 million cells, then we ran reacting with 10 million cells. So because you need to find a grid to resolve the flame. You don't need that much of a grid for fluid mechanics. What we do is that we make sure we can do non-reacting with a certain grid, and that's the same grid we use for reacting, because LEM requires a finer grid inside. So there's no need to increase the LES grid for reacting. While in a lot of papers you will see that reacting and non-reacting are done with two different grids, because you can do non-reacting with 10 million, but nobody does that. You don't need it. But yes, the non-reacting has been, the paper has the results on that. So that's one example. Another example is a slightly more complicated. This is a GE LM6000. This is one of the burners used in the power generation gas turbines. There are, in the real system, there are multiple. I'll show you some results of that. So what we're trying to do in this one is that we fix the grid around 2.2 million grid points, and I forget how many LEM cells are there, and it is a methane air preheated mixture at 6 atmospheres, so it's a little high pressure. The swirling flow coming in, and what we were interested in here was holding everything fixed, just change the chemistry. Go from 1 step to 2 step to 12 step to 35 steps. What does it? Okay, obviously, the cost is going up, and we run it for the same amount of flow through time, and the idea is to see what are we getting. Does the results look any different? Well, the results are all over the place to some extent, and there is some good news and bad news. So what I'm showing here is the top half is the instantaneous actual. Actually, the plots turned out. The guy who did it was colorblind, so then he didn't do it right, and I didn't have time to ask him to correct it. But essentially, the top half is mean instantaneous actual velocity. The bottom half is the average over 15 flow through time. And this is Westbrook Dreyer, which is a 6-step, 2-step, 6 species, 2-step. Jones-Lister, which is 7 species, 4-step. And this is a 16 species, 25-step mechanism. So they all give you the right flame speed and adiabatic temperatures. And it was done with the LEM, LES. We wanted to compare what the results look like. And again, here on the left-hand side, we're showing the instantaneous, and the right-hand side, we're showing the average. So if you're only looking at the average for this, and this is the mean velocities, you say, hey, everybody is doing reasonably good. This two-step is dirt cheap compared to, and this calculation with LEM only takes about 6 hours on 300 processors. So this is not a big, so even though it maybe you talked about 5 times more expensive, it's actually not that much. And this one takes over 24 hours. It still can be done overnight, full LES with 3D and LEM and everything, on a parallel computer. But the point was that this seems to, the two-step, which is WD2, the black line, has some over predictions here. Instantaneously, there are some variations also, but on the average, they all look the same. So that seems to suggest consistency of the chemistry for the fluid mechanics, but not so true for reaction flows on the chemistry side. Because now, if you look at this is the temperature profile, instantaneous temperature on the top half, average temperature on the bottom half. You can start seeing that even though this distance, this is the recirculation bubble is sitting here, and the flame is being anchored, by the recirculation. But you can see that this region is reasonably well pictured, but the front is quite different for different chemistries. Now these are important because if you increase the strain, these are the regions that will go extinct. This is where you get emission effects. A lot of other fun stuff happens. But on an average, if you look at here instantaneously, this is methane mass fractions. You start to see huge variations in the predictions of the models. So they, and especially as you go to the more detailed chemistry, you start to get different results. So the temperature is a result of the chemistry, but the chemistry is actually there are differences happening in the chemistry. And in some cases, for example, the reaction rates show, this is showing the reaction rates of methane. As you go further downstream, the reaction rates become very different. That means the flame wrinkling and the burning is changing just because of the chemistry, because of the multi-step chemistry. Even though the beginning point is captured properly, the region of the flame is very different from that thing. So these kind of studies are useful. So here is some more. If you start looking at minor species, is of course all over the place. That of course the two-step mechanism has no major minor species except for CO. But notice CO predictions, if SU25 is supposed to be a more detailed mechanism, is more reliable. Four-step is way over predicting CO. Two-step barely is under predicting. But as you go to here, you start seeing that the four-step mechanism actually is bad. So if you said two-step is bad, let's go to four-step. That's not necessarily true, because four-step is predicting a lot more radicals. The CO is way off, and compared to the Jones, the more detailed mechanism. On the other hand, obviously, some of these guys, this one, the CO, for this, you can see the pictures, how different this is. The Westbrook Dryer basically doesn't predict much CO at all. It's only showing a little bit of CO in the flame front, while this one is showing that most of the CO is produced at the edge of the flame. While this one is completely gone berserk. So sometimes taking a small step in chemistry, going from one step to a four-step, and you say you're doing a better job, sometimes it's not true. And sometimes you have to check that chemistry against some application problems to see whether it's worth it. Sometimes it's better to go straight to a more detailed mechanism, because if you're going to already spend 1 day computing and the other one takes you 2 days to compute, you might as well spend 2 days to compute. It's something more reliable. So that's typically the challenge you have to deal with. Another problem, which is I'm just going to show here a application of a this is not necessarily an LEM issue, but this is a type of problems where LEM has difficulty dealing with. This is like a big duct where you have an ignition flame kernel and the flame is going through these baffles and starts to accelerate. And as it accelerates, it starts to go into almost like a detonation regime, like the pressures are going up. You can see this is showing the pressure rise. This is experimental data, and this was basically using a 3-step hydrogen air mechanism. So a problem like this is actually very difficult to model from an LES perspective, because initially it is a laminar problem. You start getting turbulence as the flame starts to get pressurized and it wrinkles through these things, but these are still large scale structures. These are not small scale structures. They are being generated by these scales, and by the time the problem becomes turbulent, which is occurred somewhere down here, lots of other things have happened. So a problem like this, it actually turns out that doing an LES is actually difficult. You may need to do more like a DNS, which is basically what we were doing. This is actually a 2D calculation with 10 million grid points in 2D. So you can imagine the kind of resolution was we were resolving very small scales, and still we couldn't. The turbulence wasn't like a cascade of turbulence. Like you don't get small scales. We actually did even 3D coarse grid with a thickened flame model to see whether we can capture that, the basic behavior, and we do capture a similar behavior. But thickened flame model, if you are familiar with it, it is not a turbulence model. It's a numerical model. It thickens the flame, laminar chemistry is modified, and the diffusion is modified, but it is not a filtered. There's no closure per se of the model, so you can use it for under-resolved DNS type problem, which is basically what this is, and it's showing that it captures the same physics, although there are differences between 2D and 3D, but 3D obviously does a better job, but obviously this kind of oscillation becomes a tough problem to simulate. So I just want to show a couple of problems where the problem is not easy to model from an LES perspective. This is a case where it's a long duct, you have an ignition kernel, and the flame is propagating, and actually this shape structure has been seen in experiments, and is looking at the overpressure between 2D and 3D. So some problems like these, even though it's starting to become turbulent, and it is becoming turbulent and is actually going to be 3-dimensional, most of the initial action is 2-dimensional. But the 2-dimensional requirement, this is 50 million grid points, just for one simple calculation. Because if you did a very coarse grid, you will get nothing. It will be all wiped out. So these things, these kind of problems challenge you because it is not an LES issue, it's not a closure issue, it is a scheme and grid issue. And to get this problem. So this is a deflagration in a 10-meter long duct. These are experiments done in, this is another nice experiment. I wanted to show this because it's fun. This is like a tunnel in Swiss Alps. When the people in Europe have been worried about what happens if you have a gas leak in the tunnel and you have a mixture and the entire tunnel blows up. How does it blow up? So these were the simulation of a tunnel, literally a tunnel. You can see that. And they release some fuel air mixture and they ignite it and then they see what happens. So they have used very different models, around 6.5 million. So there were a lot of tests done, and you can see the list of codes. They use Fluent, flat German reaction codes, I don't know, a bunch of other codes. Many of them are finite volume, but many of these models use progress variable and models that were tuned to match the flame speed. So they actually had experimental data, so they matched the flame speed. We used finite rate chemistry, and we compared our prediction, which is the dotted line, against all these predictions. So overall, we are recovering within the bounds of the other code with our code with finite rate, while those guys were actually they were running cheaper. We were running more expensive because we were using finite rate. I think only, forget, some of them didn't use finite rate. Some of them did use finite rate, but most of them are, some of them are Euler codes, flux split schemes, low pressure based solvers. Anyway, there was a whole comparison. So there was a good example of showing kind of premix problems where LES is not the player, is not a controlling parameter. These are problems. So transient deflagration to detonation type problems are very difficult. It sounds very simple, but it's actually very difficult because you not only have to deal with transition from laminar to turbulent flame, but you also have to go from low pressure to high pressure. Pressure builds up. This is basically showing overpressure. Eventually, if it is long enough, it will detonate. It will become detonation. So So it becomes a very difficult problem from a modeling perspective. But let's say on some other problem, here's another example. This is a very interesting experiment that was done at Georgia Tech many years ago. It's called the stagnation point reverse flow combustor. Essentially, you have a fuel air pipe sitting there in this is a combustor, but the combustor is got a wall. I mean, there's no outflow in so the inflow and outflow are in the same location. So flow comes in the middle, it goes down as a stagnation and the products go out from the side. Okay, so you can send it as premixed. In other words, there's no air, it's all the inner pipe is closed and you just send a premixed mixture, or you can run it as partially premixed, non-premixed, and you can even do it without. So the classical scenarios, combustors are here. You have a fuel air mixture, you swirl it, you burn it. That's the LM6000 one we showed you. This is like non-premixed or partially premixed where you inject fuel, swirl it, and burn it. So the flame burns like that. This one is the opposite because it's operating in a stagnation point problem, and the question was they ran both premixed, non-premixed, and non-reacting, and the idea was can we model it with the same in the same approach. So we looked at this problem, and first thing to look at is we look at the non-reacting case. This cold flow non-reacting case. This is the data, PIV data. What is important to mention that I said it is a stagnation point flow, but because of confinement, it doesn't look like like the jet. Even the jet that is coming in doesn't act like a free jet. This blue line is the free jet decay rate, right? So that means you would assume that the jet that's coming out here should become like a free jet, and out here it should become like a stagnation point flow. You can see that the jet is following some correction. It's like a confined jet, and then as it approaches stagnation point, the flow becomes dead. Like the stagnation region is, if you're familiar with the classical stagnation point problem, it should go from free stream to stagnation point like that. In other words, the stagnation point is the only stagnation point, right? I mean, the flow becomes zero at the stagnation point. Above it, there is still some flow. The flow is uniformly reaching stagnation point, but here, because of confinement, there is a whole region of stagnation. There's like almost 50 millimeters of the domain, like some region here, everything is stagnant. So it acts like a stagnation point, but it's not a stagnation point. Yes?
The phase which has both inflow and outflow, how you are finding that? There are two angular phases or one?
Yeah, there is an annular pipe here with inflow, and then this is outflow. This region is an outflow. So flow. This one? No, this is just to show the profile. The wall is somewhere here. Because in other words, when the jet comes out like this, it goes, and you can see there's a nice turbulent spectrum on that. So then we looked at the same problem, slightly different inlet velocity. One was premix, where we sent premix mixture through the inner flow, nothing from the inflow. The other one, we had air coming out and fuel in the middle. That's a non-premixed. Equivalence ratio was the same. Temperatures were slightly different, atmospheric, and there was some, we used two-step mechanisms and two-step NOx mechanism because we were looking at NOx. It was a 7-species chemistry, so total 7 species, 12 LEM cells. This was an earlier paper done in 2008. So it kind of shows you what's happening here in the cold flow. What it's showing here is the flow comes in. Blue is negative, so that means it's going backwards. So it is not swirling. It's a pipe. It looks like it is swirling, but it's not swirling because the flow is creating jets back and forth. So the jet that is coming in is confined by a reverse flow jet. So you can see there is it's almost like it is moving around, but it's not swirling. So this is the non-reacting, and that is the reacting result. Just to show some pictures. So then we looked at this reacting problem, and this is the experimental data again showing the reacting. The reason there is a difference here is that in the reacting case, they didn't have and they had the pipe in the middle. They had left it open, and we didn't simulate the pipe in that time. So, but we can see that the decay rate is picked up by thickened flame model and LEM and even EBU. Again, so we're trying to compare. And notice here that unlike this non-premixed non-reacting case, the stagnation is almost like it kind of reaches stagnation. Doesn't reacting is different from non-reacting, and I'll show you a comparison in a minute. And this shows the mean and the RMS, shows overall there is some agreement between all methods. That tells you something interesting, that this problem is doable. So here is a non-premixed, premixed, and non-reacting comparison. The red line is a non-premixed. This is the blue is the premixed. I mean non-reacting. You can see the stagnation region is much larger. But what is interesting here is that this scenario, both the premixed and the non-premixed in the experiments show very similar behavior, like in the burning zone. And the calculations, even though there are differences here because of the way the injection is, you can see that the calculations also show quite similar effect. So this is one combustor that operated in both premixed and non-premixed in a very similar behavior, even though the entire physics is different. One has no mixing, one had to have mixing. So you would say, well, they must be operating the same way. It has the same kind of flame, must have the same kind of flame. Well, it doesn't turns out that the flame is, even though this is, remember this is the velocity field, and previously I showed the velocity and showed you that the velocities sometimes come out okay, but not the flame side of it. So the interesting thing was when we started to look at the flame, we start seeing differences. For example, this is the experimental flame. The flame is actually attached to the wall. They had no image here, but the flame was attached. This is the LEM-LES prediction. You can see that we are capturing, we don't capture the full length of it, we're capturing something like that. The thickened flame, by definition, is thickened. So you can see it is kind of wider in structure because it's broadened. EBU is completely wrong. Even though the velocity field looked good, the temperature field, or this is like the average heat release. We're looking at chemiluminescent here, so we're looking at heat release. So according to the EBU, heat release is occurring here. According to the experiment, the heat release is occurring here, right here. So EBU and thickened flame and LEM capture the structure reasonably, but LEM is thickened flame is obviously much wider, because it has been thickened, so we got a correct thing on a factor of 3. This is with finite rate and everything. The total cost was 3 times more than the other cost. You remember, thickened flame just runs the same number of species. EBU is cheaper than thickened flame, but so it's like it was expensive. But still, overall, thickened flame and LEM looked okay. The non-premixed actually turns out to be quite different. In the thickened flame, first of all, everybody knows thickened flame cannot be used for non-premixed. You have to play around with that. We actually tried steady flamelet, and it didn't even work. Gave me back, it didn't actually produce garbage results. It actually showed an attached flame that didn't even make sense. So the premixed flame was attached. What was interesting here was that the premixed flame was attached to the lip, right? The non-premixed flame was lifted in the experiment. So this is a lifted flame. I mean, the heat release is occurring here because all this region you have fuel air mixing. It is high strain. It's not burning. It's mixing. And LEM still predicted a lifted flame. The location is obviously wrong because the chemistry is probably not right. EBU again is off the chart. It's also still shows an attached flame. So LEM is predicting the flame length incorrectly, but it is mostly because the 2-step. We actually ran a 12-step mechanism later on, which gave a better result. But again, here is a scenario where the same geometry, same condition, change the inflow conditions. You go from an attached premixed to a lifted non-premixed, and LEM can handle that because even though there's no burning, you basically have mixing going on. The turbulent LEM stirring is doing all the mixing, and when finally gets lit up, it starts to burn, and then it produces that flame. So it has potential to do lifted flame, and I'll show you some other result. Another important point to mention here is that if you look at that flame, the premixed flame, it is not a flamelet, because if you look at various locations on the flame, you can see that some regions are close to broken zone, some regions are close to thin reaction zone. So the flame structure in this region, because, and why is that, is because the premix flame, you have products coming back here, going back, right? So products are mixing with the flame as it burns. So you're getting mixing of products with the reactants and the flame region. So your regime of operating in these locations are all over the place. Like 4 region is looking like a thin reaction zone, and while region 1 is acting like a broken zone. You know, so you have a wide range of combustion going on in a premix flame. Yeah. That is chemiluminescence. So it is like a qualitative comparison. Yeah, they just took chemiluminescent CH star image. So it kind of represents heat release, but it doesn't really, because the chemistry doesn't have, we don't have CH star in our model. So what we took is we took the heat release quantity from the simulation and compared it. You know, so it's not an apple to apple comparison. So, but it kind of gives you a general idea where the thing is, what the thing is. So all the images were chemiluminescence, so no real measurements. Yeah. No, EBU, we use a 2-step chemistry with the EBU. It's that EBU LES version of EBU. I didn't go through it, but you look for the minimum of the chemical time and the mixing time. So yeah, but we look at all the chemical time and mixing time. So we're running a 2-step chemistry. Typically 2-step, you have uncertainties in that. Typically the EBU is designed for 1 step. You know, so but people have extended it to 2-step, but maybe not more than that. So another one I wanted to show, this is a work that we wanted to pursue some more, but it was developed as a alternate to flamelet. So the idea here was that the flamelet, what you do, you solve the mixture fraction and you tabulate the chemistry and basically solve one equation and you get the chemistry out of that. We didn't want to do that. We wanted to carry the species, so solve for the species, but you tabulate the reaction rates for all the species. Now, if you have a 20 species, you have a 20-dimensional table, right? Which is very difficult. So what we did was we trained a neural net, artificial neural net, on that chemistry on the fly. We ran the linearity model. There are a couple of papers in the symposium and combustion flame where we ran the linearity model offline, the code that I just gave you, and stored the composition and trained a neural net on the reaction rate. And the neural net storage is very trivial, you know, so we can store the neural net. And then we tried to look at what we can, whenever we needed the chemistry, we just pulled it out of the neural net. So the chemistry cost stiffness goes away. Then we did one more step where we did the turbulent problem, the linearity, and we stored the turbulent neural net. Now I'm not going to go into all the details. The idea was to compare with the DNS, and this was a case done, it's a simple box problem, periodic problem, oxidizer, fuel. There are 2 flames formed. Reynolds number is around 4,000. This is a 11 species, 21 reaction mechanism, and the DNS was done by Sandia using 350 million grid points, very high resolution DNS. So we ran a 700,000 grid point and a 5 million grid point LES. So orders of magnitude cheaper than DNS, okay? But with the same chemistry, same problem, and then we compared with subgrid turbulence. Obviously LDKM is a KSTS model with LEM and the turbulent neural nets, and DI stands for direct integration. That's the brute force LEM LES. And then we were trying to see how much gain we get, and the reason we studied this was that this flame is initially there's a laminar flame, it becomes turbulent, then the strain rate goes up, it goes extinct, you know, and then afterwards when the strain rate weakens, it reignites. So the DNS showed both extinction and reignition, and the goal was, can the model predict extinction and reignition? LEM LES can do that or not, and that was the point. So you can see here, this is the OH mass fraction, it is wrinkling, now it's dying, it's gone extinct. But you have little bits of hot pockets left, and then as it goes weaker, suddenly you start seeing reignition appearing. You know. And this was done in the DNS, also showed that. So now I'm showing here the temperature. You can see initially the temperature is high, now it's dying out, and there's only hot products left. and then after a while it suddenly reignites because there is an oxidizer in there and reactants fuel in the middle. So so this simulation in the experiment DNS, and by the way, this is a DNS. There's no real experiment for this. What they showed was that extinction occurs after 20 turnover times, and reignition occurs after 40 turnover times. And we were trying to see whether we can recover that or not, and that's the point. But one thing we found very interesting, and this might be useful for people with who are doing flamelets. Remember, flamelets are what? Flamelets use a scalar dissipation model, right? The scalar dissipation chi. Scalar dissipation models are used for turbulent flamelets. You need to. So there's a model for that, and typically they assume that scalar dissipation for the mixture fraction holds for all species. Here, because we are running species, we could compute the scalar dissipation for each species to see how it behaves over different periods. And what I want to point out is that 20 is when it goes extinct and 40 is when it reignites. You can see that the scalar dissipation model that people use in flamelets, which is the chi, actually predicted values are quite different. At 10 it is like this, at 20 it is like that, and 30 and 40 is slightly close to that. If you look at CO follows, interestingly, the scalar dissipation, the chi, the scalar dissipation, remember this is a measure based on a mixture fraction. But if you look at the scalar dissipation for OH, it looks very different. Not looks at very different, it looks very different at extinction versus reignition. Like these two seem to be the same for extinction and reignition, while OH is showing different results. So here becomes a question, if the scalar dissipation is the same as extinction and reignition, why should it predict extinction and reignition? Nobody has done it with flamelet, obviously nobody has attempted this problem with flamelets, but if the model is not sensitive to extinction and reignition, there's no way it should be able to predict that, even though qualitatively it is similar to CO, it is way off from OH. And OH is the radical in this, that's the key heat release mechanism. So that was an interesting observation that we got to say that, yes.
What is the overall equilibrium?
This is, I think, well, it's a non-premixed system, so it's burning at stoichiometric, so this is a fuel was 50% CO, 10% hydrogen, 40% nitrogen. It's like a syngas mixture, So, but then when we actually looked at the problem, so this T equals 20 is when it goes extinct. You can see the DNS is here, the turbulent neural net is here, the laminar neural net result is the black line. The blue line, by the way, EBU is multiplied by a factor of 400. So it should not be even on this page, So it is not right. I mean, we were just showing it qualitatively. So it is way off the scale. In other words, EBU doesn't work at all, in this problem. So extinction reignition cannot be predicted. And you can see that OH is low at extinction region, and at 40 it has picked up. And this again, EBU is multiplied by a factor of 10, so it's way off. So the bottom line here was that the direct simulation using LEM, LES, and turbulent nets were quite successful in predicting extinction and reignition. And what was interesting was the cost speed up. So EBU for this particular problem, because I think this was the 5 million grid point problem, compared to the direct integration LEM, because it had now 30 species, no, 20 species, I forget 11 species or 15 species, 11 species, 21 reactions. EBU on the same grid was 20 times faster because it had just, so this is LEM, LES. The laminar neural net where the chemistry was stored, just the chemistry, was 5 times faster. The turbulent neural net was almost as cheap as EBU. So in other words, you have eliminated the cost of chemistry from LEM. So LEM, this is all LEM results, except this is LEM results. This is turbulent neural net, which uses the LEM model as a closure in here. So that was a good advantage. The other point was the table, the laminar neural net table was 2 gigabytes. The original table size was 2 gigabytes. The neural net was only 0.13 megabytes. That's the advantage of neural net. Neural net is all you're storing is the coefficient, so it is low storage requirement. Turbulent neural net was also about the same size. Now there is a bad news about these neural nets is that if anybody is familiar with neural nets is that it can only predict in the space that you have trained it for. If you are outside that net, it's going to go berserk. Like people talk about training it on the fly. You have to retrain the algorithm, you have to add more space information or not. But neural nets has the potential to eliminate a lot of the chemistry cost, which is what is the problematic for LES is that if you're doing finite rate, is the biggest headache is the chemistry. This factor of 19 is essentially the LEM plus the chemistry cost going on. So this is just to kind of tell you that this kind of problem, this is another way of doing chemistry if you can figure out. Now we are not doing neural nets because, like I said, a neural net trained on one condition, if it suddenly goes out of whack in another condition, you are in trouble. So what we are doing instead is to put the chemistry into GPUs or the Intel Phi coprocessors. So we basically put the entire chemistry into GPUs. So and GPUs as multi-threading potentially is fast enough that you can eliminate the cost of chemistry. Not eliminate, but reduce it significantly. So that's the next approach we are trying to take. Here is another interesting flame. This is a non-premixed bluff body swirl flame. So you have a methane jet coming out. There's a swirling air outside. And there was a bunch of cases. There was, again, it's an old result, but I wanted to highlight this. Again, I'm using it to highlight some. This is only one step mechanism. This was done many years ago. Now we could do it much more detailed. We ran different LEM resolutions, but the idea was to see how the flame changes with flow conditions. So one case was jet was at the jet speed was 66 meters. The methane jet was 66 meters. In another case, it dropped to 32 meters. So there was an experiment showed a huge change in flame structure just because the jet speeds were changed. And so that's why we picked this problem, because the idea was to see whether the model can see that without touching the model. Remember, we are not changing the LEM model. It's the same model. Everywhere we are using the untouched model. So here is an example of what the SM1 flame, which is the low-speed jet flame, versus the SM2 flame, which is the high-speed jet flame. So you see the jet coming out. This is a low one. You get a recirculation bubble sitting here. You get another 2 recirculation bubbles here, and the flame is pinched. In this, I will show you in the experiment. In the high-speed case, the jet is so high speed that it only gets the bluff body side. There's a bluff body here, so you have the bluff body flame. So the flame is more straighter. So this is because of the central jet speed is, and that's how it looks. I mean, for example, this is the experimental visualization. This is the image from the experiment. This is we were trying to cook up on something that, we were trying to do a Schlieren, computational Schlieren, trying to see what that is. So, but again, you can see that because of that recirculation bubble sitting here and the bubble sitting here, this thing pinches, and this is also pinching and going out like that. While in the other case, the flame is much more straighter. We don't get the close-out conditions because the grid was very coarse in this problem. So this is called a necking flame. This has a neck, while this one has no neck. The only difference was the speed of the central jet was increased. That's basically the thing. So and here it shows the so non-reacting looks like that. The reacting case SM1 looks like that, and we were able to show that some of the measurement technique we compared to the experiments. So there was some data available. And we were able to match the experiments reasonably well, in both cases, which is suggesting that the model was adjusting to the fluid mechanics. And here's there's more details in the paper. So these were kind of problems where the problems were attached flames, simple flames, but showed features that are uniquely not the same. Now, if a model cannot see the differences, then you'll have to tune it. And that's the problem. We don't want to tune the models, because the more we tune models, every problem you have to know the answer first. So in these cases, these calculations were done based on the boundary conditions, and the code ran, and then we compared. And there's no adjustment done after the fact. It was like one shot. If you do it right, you do it one run only, So that was the idea. So next thing I want to show you is something much more interesting. This some stuff that we recently finished. This is combustion instability. I know a lot of people might be doing combustion instability here, but this is turbulent combustion instability closer to a rocket engine. This is a experiment done at Purdue, and it is a long flow, and there's the oxygen is high pressure oxygen. It is at 1.34 megapascal, so it's not. It's like 100 atmospheres, 13 13 atmospheres, relatively high pressure. The main thing was that this was a oxygen tube, and then methane is injected from a slot, like some thin slot, and what they were able to do was change the length of the oxygen tube, and with that they were able to manipulate the amplitude of the oscillation. So this one generated longitudinal oscillations because there's a choked nozzle here, throat. So it's subsonic flow, high pressure subsonic with longitudinal instability. So this is what it looks like schematically. You have an oxygen coming, not hot air. This is pure oxygen, so it's high temperature. With some water because of pre-burner effect. There's methane being injected here, and we were trying to predict. And this was the frequency map they got. We got some reasonable predictions. We didn't have predictions of the peak value correctly. It turned out later on that they measured some flow rates incorrectly, so we're redoing it. But essentially, as you change the length of this pipe from 9 centimeters to 12 to 16, you get the amplitude, and the frequencies also change, and the trend is similar, and the amplitudes that go up and go down as we're seeing it. And typically this is how the flame looks. The flame is anchored. I'll talk about the physics of the flame in a minute, but this is the linearity picture that I showed you earlier. Now this is non-premixed. This is showing these points are standard. I'm just picking these points randomly, and I'm showing what's going on in the linearity, just to show there are stirring going on in here. Yes. No, there's no mass addition. That was there was only fuel was added here and oxygen was added here. Those are pressure transducers. There's no mass addition. So this is purely. It was supposed to be a non-premixed. The goal was to mimic a rocket engine. If you're familiar with a rocket engine, you have oxygen, methane. Oxygen is typically liquid, and gas is methane, and typically the flame anchors right here on this side. That's the idea. So they were trying to do high pressure oxygen combustion, but not go to super high pressure, not to go to supercritical conditions. So the assumption was that they will get instability, and they can look at how the flame is anchored. Well, it turned out that what they hoped for was not what they got. For example, here is the predicted values. I'll show in a bit. It turns out, even though this is non-premixed, it acts like a premixed flame. And the reason is that the methane is injected here, and this is oxygen, but this region, this shear layer has so much high shear that the strain rates are so high that the flame cannot anchor them. So the flame lifts off, becomes all mixed, pre-mixing goes on here, and then anchors at the base of the stem. So the flame anchors as a premixed flame, so you can see the flame surface showing here, so it is a non-premixed system with an anchoring mechanism that is by rich premix. It's not even premixed, stoichiometric premix, rich premix, because there's a lot of fuel here. So that means that later on it's going to burn. A rich premix means that there's fuel left over after it's anchored, after it is burned. So that fuel is going to mix again and burn, so you get a very complicated structure. So here is just to show you the amplitude cycle. You get limit cycle, combustion instability. Those who have done combustion instability, this is the solid line is LES, dots as experiments. You can see that we pick some of it, but not all of it. The amplitudes are not right, the frequencies are off, but the trend is similar as to what we are seeing in the experiments versus thing, that we are getting the limit cycle and it's behaving like a combustion instability, and typically that's what it looks like. You have the pressure oscillation in the combustion chamber, the pressure wave goes, bounces off the throat, comes back, and you can see here what I'm showing here. The background is pressure, and this red and blue are the CO production and CO destruction. So the idea was to show where the heat release is occurring. The CO destruction, production is not a heat release problem, right? CO, methane breaks up into CO, but when CO becomes CO2, you get most of the heat release, So the heat release is occurring in a region down there, and when we take the frequencies and look at the modes, we find out that there's three modes that are in there. First is a half mode. You can see a pressure node sitting there. Then the second mode has two nodes. And one way to look at the nodes is that you have to look at the phase also. So not only the pressure should be 0, but the phase has to shift. So you get both. So we get a standing mode, one mode, and standing second mode, and a third mode which is very weak. But in the inlet, it's a traveling wave. The wave is traveling. There's no mode shape in there, standing mode in there. So the point was that this, and you can see a limit cycle heat release. Yes. The third one is very questionable. Yes. The third one shows 3 nodes, but the phase is, it kind of lines up, 0.12, you see some phase shift here, there's another phase shift here, but from 0 onwards is the inlet. There is no mode shape, it's just a traveling wave. So it basically it wasn't surprising because they made the length of the chamber to match the modes. In other words, they were trying to trigger the instability. This was designed to trigger instability, but the first and second mode was the one they believed was getting triggered. The first mode is very clean, you can see that, and the second mode is a harmonic of that, and the third mode is a little bit weaker on that. But this is LES prediction. The experiments had similar information, but like I said, the results matched qualitatively. And here is what I was talking about: the premix versus non-premix. This is the stoichiometric surface. Right? If it was a purely a non-premix problem, you should burn right here along this black line, right from there. But nothing burns here. The white line here is the temperature 2000. It kind of represents the flame. So you can see the white line is anchored. It moves around here. I'll show in a bit. But then as it goes further down, the stoichiometric line and the 1000 line starts to meet because it's now becoming you're getting a triple point. You're getting a premix, this is a rich premix flame, then it becomes leaner, then you get a lean premix solution, and then you get a diffusion flame occurring. So downstream you're getting a triple point behavior, and the triple point turns out to be close to where the heat release is occurring, and if you kind of go through the picture carefully, the triple point moves around. And you can see this is we're trying to show you a cycle. Like the triple point, the anchoring flame tries to move in. When the pressure goes up, the flame is pushed in, but never far enough. It never goes this far because the strain is so high. But the triple point kind of moves around. It goes around in a cycle during the oscillation. And so the oscillation is I guess you could call it a chicken and the egg because the heat release and the oscillations are all tied together. So that's, and it obviously the Rayleigh criteria is satisfied. And but what is interesting, like I was pointing out, is that this is the Takeno flame index. When it is blue, it is I forgot what it said. Red is premixed. Yeah, red says when you see the index, whenever it shows red, it is premixed. Whenever it is blue, is non-premixed. And what it's basically trying to show, this is like snapshots, it's not continuous, so just not, you can't see it as a movie, but you can see that there is red and blue everywhere. The initial anchoring is always primarily as a red, but you see blue regions forming, and it is also premixing non-premixed regions in the 3D. This is a 3D problem, right? So the 3D is very complicated. So this is a problem which was a non-premixed system anchored like a rich premix flame and created a triple flame during combustion instability. So it's a very simple looking combustor but producing all kinds of complicated dynamics. So this is just to summarize the results. As you can see, we are catching the trends of the mag frequencies at different cases, but there are differences. It turned out later on that the experimental flow rates were miscommunicated. There was an error in the measurement valve, so we were not running the same conditions, but we haven't really bothered with that yet. Non-premixed also can show combustion instability, and this is just this is an earlier work. I just wanted to point out, when you have Rayleigh criteria lining up with pressure, you get instability, but in that case the flame is very compact, and when it kind of becomes very compact, this is the vortex breakdown bubble that is forming. I guess I'll skip through this. I mean, this is a old video which actually has music in it, but so this is another one I want to show because it's interesting. This is actually Tim Lewin's experiments. He did that and we modeled it. This is he may have discussed this, I don't know, but this is a premix system, swirling premix with a bluff body, right? And it was the idea was that, and it was a very complicated swirlers, and since we didn't know how to simulate the blow conditions here, we ran the full rig. The swirlers are sitting here. Notice the combustor is in a full rig, and we simulated the swirlers. We modeled the outflow of the swirlers for the combustor studies, and we ran 2 equivalence ratios because they did 2 experiments, and we ran with a 4-step 8-species Seshadri-Peters mechanism, and we were trying to compare to the. Turns out the experiment showed completely 2 different flame structures, and we wanted to see whether the model can predict that. So this kind of shows you what the complexity is. That the blades, there are lots of swirl blades. You get swirling flow coming out of the chamber, and we wanted to model it. So the first thing we found was this is one type of flame where the flame is only anchored on the inner side, bluff body. This premix mixture coming in, it is anchored on the inner side. This is the experimental visualization. This is the calculation. In fact, there's comparisons I'll show in a minute. And that means all this region has got fuel in it, but it's not. There's no anchoring going on the outer sphere layer. So if you look at the flow, we get pretty good agreement. This is the PIV expert data on the top. This is the LES. We ran the LEM. Actually, this was run with thickened flame because this was a premix problem. We ran. Thickened flame was able to reasonably predict the results. And you can see that there is quite a good agreement of the size of the vortex breakdown bubble and the locations. There are some differences, and it's been discussed in the paper. But then when we increase the equivalence ratio, the flame becomes completely different. Now you're anchoring on both ends. The flame looks like this is the fuel. The flame is sitting like that. That's the experimental flame, and that's the heat release distribution from the experiment. So, and again, when you look at the comparisons of the experiment with CFD, there are very good agreements. You get the same type of behavior. The top half is experiment and bottom half is computational. Basically, we took our LES results and filtered it down to the PIV resolution and used the PIV scaling to plot the results. So it's not like we're comparing, we're making sure it is apple to apple comparison. What is interesting was that after this was done, we wanted to see whether we can do a transition. LES is very interesting. So what we did, we started with flame 3 there, and we increased the equivalence ratio in the inflow. You'll see that as the swirl goes on, that flame will turn around, start picking up burning from that zone, and suddenly anchor there. It becomes flame 4. So this is called flame 3, this is called flame 4. So after a while it becomes just like the flame 4, and you take the flame 4 and lower the equivalence ratio, and you'll see this is near the end. So here initially it starts off like a flame 4, like in this region, and slowly as you go back, that part dies out. It becomes flame 3. So, and we ran it back and forth. Basically we ran the simulation and dynamically changed the inflow conditions, and the flame responded. The reason this is an interesting problem is that this work was done with Pratt & Whitney, and they attempted this with their codes and Fluent and many other codes. All codes predict only flame 4. No code has been able to predict flame 3. That's like a good challenge for any code. I mean, they tried many codes for that. Yes.
Has that transition been captured in the experiment?
Yes, yes. In fact, there's a hysteresis for that. In other words, experiments have done the same thing. So what we did exactly, we followed the experiment. Yeah, they have papers on it.
You did good comparison with the experiment?
Yes, in the hysteresis also. These were the steady state static comparisons, but then they also did hysteresis studies, and we have actually done 3, 4, 3, 4. Like we went from 3 to 4 to 3 to 4, and every time is a slight difference in when it recovers. And we didn't complete a lot of the run because the student graduated, but we were starting to get the same hysteresis pattern that the experiments were getting. They did more comparisons. They have papers on it, more papers on the experiments and the modeling. After we got these results, we got fired. So our funding was. They were happy with our work. They didn't have anything else for us to do, so we stopped working on it. So. Yeah, the fuel was increased. The fuel was increased upstream. So in the premixer. So basically, as far as we are concerned, we just ramped up the equivalence ratio, for our application. But that's basically what they were. They had a big premixer upstream. That's where they changed the fuel. Well, the wall temperature is also included because the wall did change temperature. It's an isothermal wall. There's a wall temperature was measured. But it was a combination of both because basically, if you could think about it, as the equivalence ratio is high, flame speed is high, so it wants to come back in, and when the wall is hot, it can light up. This is not lighting up; it's not igniting. It is a flow. The flow is picking up some features and bringing it around. So, and when it was lean, when it becomes lean, then it becomes too weak to come up. So even though the wall is hot, in both cases walls are hot, measured temperatures. The only information we had was the wall temperature and these images. The boundary conditions were not known. So we had to simulate the full rig. We had to do the full geometry. We had to do this full geometry first in order to get the conditions here because this region was not known. So upstream was known. The flow rates were given. The geometry was given, but we didn't have any inflow conditions. So we had to predict that first in order to do the modeling. So that becomes. No, they gave us wall temperatures and the block body right here. So we put an isothermal wall. That's it. It was adiabatic everywhere else. They had a thermocouple here and thermocouple here. So they gave us some, and we just assumed it is the same value. It wasn't that hot. Well, we tried that in wall. Yeah, it does have some effect, but not that much. In other words, in our case, it didn't go back completely to that flame, but it was not. In other words, it wasn't going to flame 4 like what you're saying, right? There was some effect, but it turned out that the other codes will never give flame 3 would never appear. Like if you were running flame 3 with the adiabatic wall, shape will change. It would change a little bit, but it wasn't matching the data. But it didn't look like this. It was slightly different. I have no idea. I mean, they were running commercial codes, right? I mean, they're like fluent. They were running the same problem. We gave them the same grid and same boundary conditions. We even gave them our restart solution. But every time they ran it went back to this flame. I mean, this flame is very easy to get because there's a recirculation here. Almost any code will give you that. But very difficult to get that flame, that kind of flame. Remember, this is all reactants. This is all premixed. Hot premix, but it's not burning. It's not burning. There's a lot of fuel sitting here, but it's not burning. While in this one, it's all products here. It's only fuel is here. Which is the classical, swirling flames. So it was a good, interesting experiment study. So I'll show some more. I guess 11, 12, 30. Okay. So here are some other results, which is again from Christopher B. because he ran a lot of studies. He runs it with his own code, which is a version of OpenFOAM. This is Cheng's low swirl burner. Maybe some of you have seen that. Again, he's running cold flow and partially different models. It was the continuation of the same work and trying to look at how the flame burner solution looks. And you can again, it's not the pictures are so crowded. I wanted to have it blown up, but you can see that the G equation type models and EDC type models really start to have a lot of errors very quickly. The partially stirred methods seems to be the most, and the thickened flame also seem to work, because this is a premixed system, This is the other one. This is the LM6000 that I just showed you, but he ran earlier studies where we compared actually with my old G equation result with the two-step finite rate chemistry with Grinstein's and two-step Christopherby, and again, qualitatively, that G equation, the flame speed was matched, was set up. This was done a long time ago, so this is a pretty high Reynolds number problem, But he took this a little further, and what was this? Oh, this is another swirler configuration. So these are all done by unstructured solvers, or I do structured solvers. So let me skip through some of these. You can look at it later on. These are available in his papers. There are papers cited there. One interesting thing was that he took that LM6000. The actual LM6000 has multiple burners, like 16 or. So he took that same thing. He had his code rotate it, and he basically created I don't know how many burners, and he was trying to see how much sensitive the results were, and yeah, so he compared a single burner. So the question always comes up: if you have 36 burners, do you have to study 36 burners, or can you just do one burner and then extrapolate from 1 to 36? And he was trying to see whether that's true or not. Obviously, showed out that there's a lot of inter-burner interactions, that no single burner behaves the same as the original single burner. So the laboratory single burner studies really didn't help understand the more complicated burner. For example, when you start looking at it from a transient problem, you start seeing transverse modes appearing. It's not unstable. I'll show you an instability in a minute. But you have waves going around which interact with each of these burners to make each burning zone quite unique. Statistically, they are not the same at all. And that becomes very challenging, because if you want to do this is like a real combustor, real design hardware. This becomes a very difficult problem. It's expensive. It is not. You have to, and usually there's not much data in it, but on the other hand, if you just took one guy and looked at it, it doesn't seem to have the physics. So that was another interesting part, and he just, there's some information. Small modifications make big differences to the changes in pressure drop, and which is why multi-burners can easily get into transverse instability, and I'll show you an example again. Here's another example of what he did, which is kind of a helicopter engine called Caesar engine. These are all European designs, so we don't get it in US, and so it's got multi-burners again, and this was supposed to be liquid fueled, but he assumed it to be vaporized, so non-premixed. The previous one was premixed. This is non-premixed. There were 12 burners, and the idea was to see whether he can mimic it. So he went from 2 million to 8 million for a single burner, and 25 to 100 million for the multi-burner, which 100 million is not that great, because you're 12 times 8, basically doubled. He put the same amount of grid. So he still thinks the balls were not resolved properly. But he was using Jet A fuel, 18 species, 46 reactions. He even ran 561 species, 2,000 reactions. So these are very painful calculations, and the bad news is there is really, he's got some papers here, but bad news is that the cost of this is so horrendous that typically you end up doing the 7-step type mechanism, simpler mechanism, because if you want to do multi-burners, you have to do reduced mechanism. So, and again, he got, he was showing that the burner-to-burner interaction becomes a very serious problem for multi-burner thing, that a single burner analysis is not sufficient. So I'll skip through some of this. He's got some details about how things become complicated. You can look at it in the thing. Then the last one I want to talk about is from Terry Poincel's group, and he looked at combustion instability again. Yes. What? But basically, when the flames are interacting, you send out pressure waves from each burner. So each burner is oscillating. You're having disturbances from each burner. So the pressure waves are moving around. So this burner interacts with this burner, and this burner produces another pressure wave. It goes around in circles. So the transverse is not unstable because these are stable combustion, but you get waves now moving back and forth because the flames are not. If you look at it carefully, the flames are actually fluctuating back and forth like this. In the sense that it is doing like that. So when it does that, it produces a disturbance here. This one produces a disturbance, and then if it goes into some kind of phase, you start getting waves moving in certain direction. And typically, if it is in the right frequency and right mode, you can go into combustion instability. And that's what I want to show next, where you can actually trigger transverse instability. The one I showed you was the longitudinal instability. But typical burners, multi-burners, nobody's interested in. Longitudinal instabilities rarely exist. It's the transverse instability that's very fundamental to these problems. Multi-burners are always, that's why many of the old combustors and gas turbines, aircraft engines had annular burners. Like these are annular burners. That means this burner can talk to this burner because of the annular thing. But there were old designs where they were all separate to isolate them. So nowadays they actually do experiments where if it starts to go unstable, you tune one of the burners to operate at a different flow rate, and that kills the instability. But it's again not very well understood. That's one of those very fundamental. There's been some papers on it recently, but it's still not. So this one is he's talking about very difficult, and I guess I will skip through that. So here he's basically also showing again the same thing. We all try to do the same thing. He ran 7-step. 100 million cells, 2-step 100 million cells, 50 million cells. So grid and chemistry still plays a role. Now these are AVBP, the French code, and it is thickened flame model. Okay, so this is not LEM. I haven't attempted these problems, and so he was trying to see whether he can deal with. He was talking about why we want to do compressible LES rather than doing acoustics linearization. And he was running this, again, an annular burner. There are multiple burners with 42 million grid points. And he gets combustion instability. It is an azimuthal instability. That means the instability is growing. You can see initially starts off, then ramps up, and then starts to become limit cycle. And that's why I was mentioning, if you take the standard value without the azimuthal mode, there is no oscillation. No azimuthal velocity is 0. The mean value will show up somewhere like this during limit cycle, but the variation is very different than the mean value. So the mean value really has no physical problem. So when he ran this calculation, and there's a paper, he has a lot of papers on this, you get this mode shape that is oscillating, and here is a flame. You can see the flames are interacting, and he's got explanation as to what this is going on. And basically, in this scenario, that's what's happening. The flames interact, it creates a disturbance, that triggers another disturbance, that creates another disturbance, and if it is in the right order, he's later on shown that if you turn off one of them, it might change the picture, because instability breaks down. In fact, he talks about, that is what he's saying. Oops, sorry. An azimuthal wave passes a sector, this sector. The flow rate in the swirler changes because the wave is pushing the flow. Then the reaction rate changes after a little bit time later, and the reaction changes when the pressure is positive. Then that triggers the amplitude growth, and that goes on and goes on. So.
Should be away from that burner, one element, because it is expanding and then only. But whatever you are showing, it is very near to that burner region itself in right away.
Yeah, well, the interaction according to him, according to their calculation, is acting right here. Yeah, very close. But this is an azimuthal. Obviously this is an experiment calculation they did, but they're getting interactions right around here.
Again, one philosophy could be like the region of the influence can be predicted for one. Means you can space it
Yeah. In fact, that is the point. In fact, most systems do not operate the same way. In fact, in most experimental devices, and usually it's based on some mechanics, personal knowledge, and experience. He goes and tunes one of them slightly different, and it gets.
Acid got an influence to the equivalence ratio, because some Russian philosophy, what they do, they will stagger the mixture ratio.
Yeah, stagger the mixture rate. Yeah, I mean rocket engines do that a lot too, because, but the problem is from a prediction point, if you change the design, you'll have to do the experiment again to find out how to do that. And the question was that if you can numerically do that, then it's easier to play around with this without building anything, right? And then you can figure out whether you can get a sustained stability. But this problem is very difficult, computationally is very difficult, experimentally is very difficult. But the interesting aspect is that azimuthal instability is the fundamental instability of interest. In longitudinal ones used to be important in the old ramjet type problems, but not for gas turbines. It's the azimuthal ones, and rockets also, it's the azimuthal instability that becomes severe. So anyway, with that I'll stop this lectures and take some questions. Yeah.
Last session you mentioned that if you are going from fine grid to coarse grid, it's okay because we just eliminate some turbulent eddies. Okay, but if we have fine grid, coarse grid, and after that fine grid, there is a problem because we artificially generate turbulent eddies.
Right, yeah.
In block body Volvo afterburner, there was coarse grid after that fine grid.
Well, it wasn't really a core, it was stretched grid. Those grids were stretched. When I say fine grid, you have hanging nodes, the grid lines end.
The example of afterburner Volvo, I mean that's block body.
Yeah, those were, the Volvo experiments were done with it had structured grids. So the grid wasn't like a coarse to fine. It was still, the grid lines were still there, it was just clustered.
And is the grid size in the Taylor scale in the whole computational domain?
Yeah, so these were all this work was done with like grids like this. In other words, this is actually a different grid, but when the Volvo one experiment was done, sorry.
Yeah, this one.
Yeah. There's a grid. So this grid is actually uniform, continuous. It's just clustered, But my work was using structured grid. So the grid, when I say coarse grid with fine grid, the grid lines will be hanging, like it will be like disappear. This grid line is still going all the way. It's just that it's variable grid.
All grids are in
this is a single grid. Yeah, this is a single grid.
Okay, thank you.
The grid to grid coarsely requires hanging nodes. I mean, the grids are just line disappears. So you have one grid and suddenly you have a grid twice as big, like that.
Thank you.
Mm-hmm. This was perfectly, numerically it was from exactly the same, but the way he did the ignition might have triggered it, So numerical, could be anything, nobody knows. I mean, this was, the fact that he got sustained instability is one thing, but beyond that, we don't know. So.
Which you have shown. The basic idea is that the main flow or the sees the reverse products and burns actually.
Yeah, it's like it's like an afterburner. You're using a hot products to keep it hot, right?
Yeah. Yeah. In that case, the dominated scales actually is the chemical scales. For example, auto ignition scales can be based on the temperature.
That's right.
But it's quite surprising to see your results that with a two-step mechanism, main mechanism, we are able to capture the most of the flow physics actually.
Yeah, because I think that's partly because the combustor was kind of tiny too. It's a confined system, and at least in premixed case, the flame was anchored right there. So once you have a nice anchored flame, a two-step will do a good job. But we ran with a 12-step also, and it gives a little bit better. The non-premix was the one that showed a lifted flame. That's why the lifted flame was not accurate.
But even there also, the results are quite good.
Yeah, it's good.
I was quite surprised to see.
Yeah, I think that's because the chamber was tiny. Maybe there was a help from the confinement that everything was not it wasn't auto igniting. It was actually burning, as a diffusion flame for the non-premixed, lifted flame. So it was behaving like a regular flame, So. Yes.
Can we separate the spinning component from the thing?
Oh yeah, yes, in fact, Combustors, they have actually done that. They have papers on that. You can take a Helmholtz solver and actually analyze the whole flow field and extract the mode shapes and why is it spinning, what is the wavelength. They have done that. I have not done that. Point source group. Point source group. They have a bunch of combustion flame papers. I have not done it, but I'm not sure whether they have done it. This is not this guy. I know he hasn't done it. He's just done the simulations but Christer had Terry Poinsot had a more recent paper where we're looking at different mode shapes of this rig. Trying to figure out what is the standing mode versus the spinning mode. But I have not. There's some recent papers in combustion flame and. You may want to check from this group.
You have shown that combustor, that type 3 flame I thought.
But if you see, basically, that combustor, the flame is going to hit the wall.
Yeah,
But that is not usually a design practice which is followed, no?
No, this is a laboratory combustor. That was the whole, it's just that combustor, that Tim Lewin's rig, exhibited these flames, and they repeatedly exhibited the flame. Like you're right, in reality, nobody would want the flame to hit the wall, right? So it's just that they were not interested so much on being a real combustor, but they were looking at flame dynamics. So that the idea was to see whether the model can predict the different flame shapes. That was the only part.
Usually, what is the
Type of time levels they operate these combustors?
Equivalence ratios?
Not equivalence ratio. How much duration they will be operating?
Oh, this combustor runs for a long time. In the lab, they run it for hours. Because they're nothing that is very lean. Its equivalence ratio was 0.5 something, so it's not very hot.
Okay.
I guess they can handle that. So.
Thank you.
Is somebody else?
The stagnation point reverse flow combustor, it has a reverse flow which is very close to the mild combustors that have been studied even by Norbert Peters. So how close it is, the configuration seems similar.
To which combustor?
Flameless, mild combustor.
Oh, flameless, yeah. In fact, this was originally supposed to be a flameless combustor. Turned out that it had a flame. Yeah, in fact, the idea was to mimic a flameless combustor. Because the whole idea was that the hot zone, you inject the fuel, the hot zone just burns it, but it didn't behave like that. That's why the original idea was to go for a flameless combustor, but they never got it to work as a flameless combustor. But then when they ran these things, they found that they actually ran even spray in this thing, and they found that main advantage of this combustor, according to their data, was that they got very low emissions. That was the point, this was like an alternate to the flameless combustor to get low emissions. CO was like 1 or 2 ppm or something like that, and NOx was very small, but I don't think anybody's buying that yet. It's a laboratory system. Yeah. In fact, the problem was that I don't think it can even be scaled up, because then everything will change,
I have a question. Like in some studies, people what they do is in LES they force the flow, and then they get the flame transfer function out of that, and that is what is used for doing acoustic study. So can you comment on that? That what could be major pitfalls or some potential issues that we should be careful about doing this type of studies?
Well, the flame transfer functions are dynamic. In other words, you're basically getting some number of transfer function after you're post-processing it, right?
Yeah.
So, and then the question is when you incorporate coupling to the flame transfer function, the acoustic analysis, the coupling should be in the same mode as in the real system. That's usually where I think they have a problem with. And then I'm not very familiar with all the latest flame transfer functions, how they do, but like the impedance boundary conditions,
Yeah.
like if you don't have the right impedance, and the impedance has to change with time, in the real system is all unsteady, right? So, so if you have only an impedance that is changing at a low frequency, but you have a high frequency information that has to be brought in, those have to be built into your transfer functions, So, I mean, I don't think people do that, or maybe they're doing that, but we have looked at impedance of these combustors, and the impedance are not uniform, it changes, cycle to cycle. There's a lot of structure to the impedance variations, So how much knowledge you need becomes questionable, when you simplify, you're losing something, right? So the question is, can you live with a low frequency, just standard transfer functions, or do we need to put in a time dependent transfer function? That becomes the problem, So I don't have an answer, which is the best solution, because I can post process from these simulations and give you a transfer function and impedance, and it's varying all over the place. And you'll have a mean value and a different frequency, but you'll have a lot of structure to it, So only way to do it would be to somebody to run for different structure of the impedance and see if the results are sensitive, but that's a big effort in itself. So, but that may be something, all this data has all that information, because this is full 3-dimensional in time, That's what I was saying in the beginning, how you post-process becomes a big issue. Like if you want impedance, I have to rerun everything, I didn't store that stuff, so it becomes very question. So what you want to know, you better ask first, so before you start running these things. So.
Thank you.
Okay. All right, thank you.